Okay, I want to go over some MassHunter basics, the data analysis method that we are using right here. And what I'm showing here in this screen is just the regular MassHunter screen, data analysis screen that we see even if we collect, as we collect data. The screen, the program, the display has three main parts to it. The first part is the table, the batch table full quant. So everything that relates to sample information, that relates to the analyte information, as well as the internal standards that we measure. We have two more parts of the screen. One is the stability graph, and so we can switch here to the stability graph, for example, the internal standard and our quality control that is not displayed as right now. We can do that later. The last part of the screen relates to the calibration curve itself. As long as we have our sample cursor somewhere below where we actually started measuring anything calibration curve related or sample related, we will see the full display of the full calibration curve. Just want to quickly go over what is happening, how can we manipulate what we actually look at in this main screen, in the full quant screen right here. We have columns for each of the information for the sample, the analyte, and the ISTDs that we can change. We can choose to view what we want to look at and later export. There are 4 user settings that can be defined. This one happens to be user setting 1, and what I have set for user set 1 is everything that we export as raw data. It has all the necessary information that can be important later on if we look at data and want to reanalyze them. It has for the sample, it has the standard, the data file, the sample name, the acquisition time and date, the type. So is it a calibration standard, or is it a sample, or is it a quality control? Has the levels for the calibration standards, which vials in the auto sampler were the samples in, and then the total dilution. It for the elemental information, it has the concentration in the unit that we have defined in our full quant table. It also has the counts per second, which are important for us at some points, and it has the relative standard deviation of the counts per second. For the internal standards, because we don't measure any concentrations, it only has the counts per second and the relative standard deviation. So this is something that we export as raw data. I have other definitions, or I have other column settings set up that we also either use or export. In this case, it's another view of the data that we export. We export this as raw simple. Here we have a simpler display that is then easier manipulated in our final Excel sheet to yield the results table. So we can see here just has the sample name, the acquisition date, the total dilution, and then just the concentrations for the sample. Remember, we determine our own coefficient of variance. We do not use the relative standard deviation. From those 3 measurements, we have our own coefficient of variance that we calculate, and then it also has the internal standards. The 4th setting that I use, I don't use the 2nd setting, which has the counts per second only. The 4th settings that I use for my own information has for each data point that we, or for each sample that we measure. Remember, we measure 3 replicates. For each replicate, it has all the information that we need. Has the let's just take a look at the internal standard, for example. So here's germanium for, if you take a actual sample here, so there's germanium here that had a counts per second, an average count per second of 85,650 with the relative standard deviation of 1.1%. The individual 3 data points that we collected were these 3. If they would vary dramatically, for example, this would be, instead of 86,000 or 85,000, it would be 120,000, and it would only be this element, the relative standard deviation would be huge. What I could do in this case is I could just say, okay, this is clearly an outlier, it doesn't belong here, something must have happened, and I will ignore this value. And so I will ignore it, and then it will recalculate the relative standard deviation for this internal standard. I can do this with each element. For each element where I have something similar, I can simply ignore it. For example, here I have done this for copper. And so it seems like we have excluded a value for copper everywhere, or excluded a value for these everywhere. So replicate 2 was excluded everywhere in this measurement, and I can include it again, and we can see what comes out. So then I have to reprocess the batch, and we'll get updated values. So this is what I have the screen for, but it's nothing that I export. It's just if I have a value that I'm concerned about, this is where I can check whether it's a fluke or whether this is real. The other 2 items on the screen, I just quickly want to talk about the calibration that we have down here. The calibration, of course, is what it is. We look at the quality of our calibration curve. There are like blue points right here. The blue points correspond to in what mode the detector measured. So this is called pulse, while green is analog. There is like a pink measurement is when it like switches from pulse to analog, which is just a measure of if too many counts per second come into the detector, or too many counts come into the detector, then it switches modes just to a less sensitive mode. But each calibration curve has their own values that are important, that we also export and report to our clients, which is of course the R value. The R value is the quality of the standard curve. This is a linear regression. This is just the value of how well our curve is. 1.0 is the best it can be. 1.0 is what we always strive for, and most often with most calibration curve is what we get. With most these elements, these easy elements, is mostly what we get. About like 0.9998 to 1.0 is usually what we get. Other information is the detection limit, and this of course depends on like how well an element ionizes, how many counts per second. Basically, how many counts per second do we get per ppb? The more we get, the more sensitive the more sensitive we can measure the element down to, and the lower our detection limit is. The detection limit is usually lower than the background equivalent concentration, and the background equivalent concentration is basically, or it's not basically, it is the calculated concentration of our background counts. So the background counts for copper, for example, let's just see, like in our blank verify, let's just see, our background counts for copper were about, let's say 600 when we started, 500, 600. So the background equivalent concentration for these 600 counts would be about 33 ppt. The detection limit for copper goes much lower. The detection limit goes to about like 8.8 ppt, and that just means that, of course, if we have a background equivalent concentration of 33 ppt, then another 8 ppt will increase the total counts for copper. And so we can detect that, and we do detect that. And this is the detection limit for copper. Down here are just the table displayed what the calculated concentration versus the theoretical concentration is. The calculated concentration as in like the measured concentration, and there are counts per second and so on and so forth. Then there are other self-explanatory and display options right here. Like I said, so we can scroll through each element right here, see what we have. We never change any of these right here. This means that we use the internal standard to calculate our curve, meaning that if there is a difference or a big difference in the internal standard, then that will be reflected in the concentration. So the internal standard count is considered in when this calibration curve, or when this calibration was done. So it is considered every time. The display of the quality, of the stability graph of the internal standard really is it is important to see that it was nice and flat. What we are looking for are big variations greater than plus minus 20%, which are those lines right here. And we can see that our internal standard performed well. They should be, because the samples are all pretty much the same samples in the same matrix.